Great. Well, thank you very much. This is Tom Spath. Welcome to the EPA's monthly webinar series for small drinking water and wastewater systems. Today's topic is disinfection byproducts, regulatory issues, and solutions. We have two speakers, as I mentioned before. Michael Finn will be our first speaker. Michael is an environmental engineer with the Office of Groundwater Drinking Water in the Drinking Water Protection Branch. He joined EPA in 2001 to work on the development of the Long-Term 2 Enhanced Surface Water Treatment Rule, the Stage 2 Disinfection Byproducts Rule, and the Groundwater Rule, and the related guidance documents for those rules. Michael is currently working with states and public water systems on the implementation of those rules, microbial water treatment issues, alternative treatment technologies, and water availability and water efficiency in public water systems. Prior to coming to EPA, he was with the California Drinking Water Program as a field engineer in the San Francisco Bay Area. Michael holds a Bachelor of Science in Environmental Resources Engineering from Humboldt State University. He is a licensed professional engineer in California and Maryland and a certified water treatment operator. So with that, I'll hand the podium to Michael for his presentation.
Thank you. Thank you, Tom. Good afternoon, everybody. Topic of my presentation to start us off is disinfection byproducts, the Stage 2 regulations, review and implementation. We'll try and review the existing requirements, what the rule consists of, hopefully review for everybody, and then some of the implementation issues we've been helping people with and some of the questions, answering hopefully some of the questions people have as the rule is finally implemented. Start off with some quick definitions so that everybody either remembers or we're on the same page. Some important ones for this presentation, Stage 2 in particular, the combined distribution system, which are interconnected distribution systems consisting of a wholesale system and consecutive systems that receive the finished water from their wholesale system. A consecutive system is a public water system receiving some or all of its finished water from one or more wholesale systems. And a wholesale system, to complete the combined distribution system, is a public water system that treats source water as necessary to produce finished water. Finished water is an important, in this definition and the previous definitions, producing finished water, then delivers some or all that finished water to another public water system. Another important part of Stage 2, we have multiple computers running here. Another important part of Stage 2 is the dual sample set, which is two samples collected at the same time and location, with one of those samples analyzed for total trihalomethanes and the other sample analyzed for haloacidic acids of 5-HAAs. Finished water, again, an important part of implementing this regulation and others. Is defined as water introduced into the distribution system of a public water system intended for distribution and consumption without further treatment, except as necessary to maintain water quality in the distribution system. And the compliance part of these regulations, another important part is the locational running annual average, or LRAA, which is the average sample of the analytical results for the samples taken at a particular monitoring location during the previous 4 calendar quarters. Okay, again, quick review here of the maximum contaminant levels for the Stage 2 disinfection byproducts. They are the same as everyone's been used to dealing with under the Stage 1 rule. However, the compliance calculation has changed, as we just talked about, from a running annual average system-wide to a locational running annual average. TTHM MCL stays the same at 80, 80, 60. The bromate and the chloride MCLs are also the same. Important difference between the Stage 2 rule and Stage 1 is population-based monitoring. This is an important part, was an important part of actually developing what you see in the sampling schedules. It's required for both the initial distribution system evaluation, which we'll talk about, and ongoing compliance monitoring. Population-based monitoring is based on system population and source water type, with the goal here of targeting DBP problems areas based on a better understanding of where they occur and how they form within a distribution system. Developed to ease the implementation for both systems and states and to provide a greater equity of public health protection by identifying where DBPs occur and how they're formed and the population exposed. Monitoring concept addresses issues associated with part-time treatment plants and sources, systems with multiple wells, the consecutive system issue, which we'll talk more about, and under the previous regulatory structure, some systems were taking too few samples or were taking too many samples to accurately characterize the DBP occurrence. Quickly review the IDSE requirement. Although that part of the rule has since passed, there is still some connection to which we'll talk about in terms of newer systems and changes in systems. But the purpose was to determine the locations of high TCHM and HAA5 concentrations to the distribution system. And those results were used in conjunction with Stage 2 disinfection byproduct compliance monitoring to identify and select the Stage 2 disinfection byproduct compliance monitoring locations. Another important concept for this rule and for others is what is a combined distribution system. The intent of a combined distribution system is to treat a number of systems, connected systems, as one system for monitoring purposes. The state may determine that a combined distribution does or does not include certain consecutive or wholesale systems based on a number of factors that include whether the connections are emergency connections, so the system is receiving water from a wholesaler or delivering water to a consecutive system only on an emergency basis. Or another exception would be a small percentage in volume of the total water supply, so only a small percentage and a small volume was received from a wholesale system or is delivered to that another consecutive water system. Another important point, very important part with combined distribution systems is that monitoring as a combined system requires state approval of the monitoring plan and the schedule and concurrence by the EPA administrator, which is delegated to the EPA regional office. So combined distribution system monitoring plans require 2 levels of approval, both the state and the EPA through the regional office. As I mentioned, the IDSE, or Initial Distribution System Evaluation component of the rule has passed, or expired. Those requirements are finished a while ago. All systems would have done their IDSE or the equivalent. So the question comes up of what about new public water systems? What about systems consolidating into a combined distribution system, or adding new consecutive or wholesale connections, or new service areas, either after their initial IDSE or new systems which had not completed an IDSE. That was hard. For new systems, all systems are required to have a monitoring plan. That monitoring plan includes the dates, locations needed to meet the Stage 2 requirements, and the sample site selection for that monitoring plan should be consistent with an IDSE. States can require modifications to sampling plans for new or existing systems. The state could require an IDSE-like evaluation or review for new systems as a process in selecting Stage 2 monitoring sites. There's also a requirement for consultation with the state for any changes to existing plans. And that would include a new service area, new interconnections between wholesalers and consecutive systems. And monitoring plans, this is important for combined distribution systems, are required for each system in a combined distribution system. And the state can require modifications to those plans as needed. Okay, Quickly through the monitoring frequency and locations. I'm not going to read through all these. These are in the slides and in the regulations. Monitoring requirements for smaller systems range from 2 per year for the very small up to 20 total during a monitoring period. That's quarterly monitoring for the large systems greater than 5 million. And the previous slide I should go back to, important, that's for surface water systems or groundwater under the influence, or systems, consecutive systems that purchase that surface water or groundwater under the direct influence supply. Monitoring frequencies for the groundwater systems or systems that purchase that groundwater are somewhat reduced. Again, not much for the small systems for less than 500. 2 locations per monitoring period, that would be a year for systems serving less than 500, and then up to 8 locations per monitoring period for the very large systems, again, every 90 days. Compliance calculations are based on quarterly monitoring. If the system is monitoring quarterly, they make compliance calculations at the 4th quarter following the applicable compliance date, and this would be systems that would have started after the initial implementation rules, so that part would have been finished. Subsequent monitoring and compliance is making compliance calculations at the end of each subsequent quarter. So each quarter, calculating an LRAA as a basis for compliance. For systems that are monitoring less often than quarterly, the initial monitoring included the first compliance date taken after calculating the first compliance date taken after the compliance date. Continuing compliance, if a sample is less than or equal to the MCL, the system is in compliance. If a particular sample is greater than the MCL, the system must begin increased monitoring. That's go back to quarterly monitoring. However, it is not an immediate violation. Systems that are allowed to perform annual monitoring under the Stage 2 rule must increase to quarterly monitoring for any sample, TTM sample, HM sample greater than 80, or an HAA5 sample greater than 60, or I should, units right, 0.80 milligrams per liter or 0.060 milligrams per liter. A system is in violation of the MCL if either GTHM or HAA5 locational running annual average exceeds an MCL after 4 quarters of sampling. So the LRA calculation that exceeds an MCL after 4 quarters, the system is in violation. Systems return to routine monitoring after they have conducted increased monitoring for 4 consecutive quarters, and the LRAA, locational running annual average for each monitoring location, is less than 0.60 for TTHM and less than or equal to 0.050. I'll repeat that, I missed the less than. Less than or equal to 0.060 and less than or equal to 0.05 for HA5. The allowance for reduced monitoring is a locational running annual average less than or equal to 0.04 milligrams per liter for TCHMs and less than or equal to 0.030 milligrams per liter for HA5s at all monitoring locations. So each monitoring location within a system, the LRA for each of those locations is needed for reduced monitoring. And there's also a requirement that the running annual average TOC level before any treatment is less than 4 milligrams per liter at each treatment plant. This is specific to plants and systems using surface water or groundwater under the direct influence who are currently monitoring TOC at least every 30 days. Again, I won't go through the chart here. The minimum number of samples for the smaller systems using surface water remains less than 500 do not reduce. For those systems between 500 and 3,300, one sample and one HAA per year, ranging to the very largest systems. Larger systems greater than 10,000 every 90 days, with the number of samples, sites, and sets increasing as the system size increases. Groundwater systems, less than 500 every third year. Important note here is that this is a change from the stage 1 requirements, where systems larger than 500 could reduce to every 3 years. In this case, revision, only those systems serving less than 500 and serving groundwater may reduce to every third year, again ranging from one sample at one dual sample set, which we talked about, that's a TTHM and an HA5 at the same location for the very smallest, ranging all the way up for the larger systems. Consecutive systems are an important part, some changes in this rule and some specifics in this rule for consecutive systems. The stage 2 requirements apply to consecutive systems that deliver water that has been treated with a primary or residual disinfectant. Important word is deliver water that has been treated. Monitoring, reporting, and MCL and operational evaluations remain the same for consecutive systems. And consecutive systems that do not add a disinfectant but deliver water treated with a primary or secondary disinfectant must continue to meet the stage 1 maximum residual disinfection levels, which we'll talk about for chlorine and chloramine. Again, we talked about the combined distribution system compliance. It is allowed, but each system within a combined distribution system must monitor. And another important point is consecutive systems are public water systems under the Safe Drinking Water Act. And the consecutive system is fully responsible for compliance. Consecutive systems, even though they're receiving treated water, can take steps to reduce disinfection byproduct levels and formation in their distribution systems. And those steps could include water age management, storage management, changes of valving in zones, changes in residual or booster disinfection, distribution system operation, optimization, which we'll talk about, and switching to chloramine for residuals if needed. Operational evaluation levels are also an important part of stage 2. Why do we have an operational evaluation level? There are concerns about higher levels of disinfection byproducts in the distribution system that are not identified because of the results of averaging samples. An operational evaluation is a chance for a system to evaluate its operational practices from source all the way to treatment, to identify opportunities to reduce disinfection byproduct concentrations in the distribution system, and it serves as a pre-violation warning that the system may violate the LRA depending on what actions they take and what happens in their system. It also serves as an information resource for states to use in sanitary surveys, in their evaluations of treatment, and any technical assistance they're providing to the system. The expectation of the OELs, or the operational evaluation levels, is to reduce peaks, reduce exposure to high DBP levels, and the potential health effects for all consumers. Quickly, the calculation, current quarter's results times 2, sum of the 2 previous results quarters divided by 4, average operational evaluation levels are exceeded during any quarter during which the operational evaluation level is greater than the TTHM or HAA MCL. Again, if the system has operational levels higher than the MCL, the system must conduct an operational evaluation. That evaluation must include storage tanks, excess storage capacity, flushing in the distribution system, any changes in sources or source water quality, any treatment changes or problem with treatment that may have contributed to the TTHM and HAA5 formation. And a very important component is what steps the system could take to minimize future exceedances. States are allowed to limit the evaluation if the cause has been identified. However, the steps to minimize the exceedances still need to be addressed. Operational evaluations from consecutive systems should include consecutive system actions that could reduce DBP events. including water age management, flushing, changes in valving or zoning, and management of storage and cycling changes in pumps. Continuous communication and exchange of information regarding the treatment that's occurring and operations is important for both the wholesaler and the consecutive system to meet their reporting requirements and to take steps to reduce exceedances. The best available technologies for disinfection byproducts are identified for systems that disinfect, that is, enhanced coagulation or softening, resulting in TOC reduction combined with GAC10, nanofiltration with molecular weight cutoffs less than or equal to 1,000 Daltons, and please don't ask me what a Dalton is because I won't be able to answer the question, and GAC20 as a separate component. Consecutive systems that buy or receive disinfected water, the best available technologies for those systems serving more than 10,000 people is improved distribution system management and storage tanks management, decreasing residence time, and plus the use of chloramines as a residual disinfectant. For those systems serving less than 10,000, the best available technology includes improving distribution system and storage tank management to reduce residence time. What about proactive measures to reduce DBPs before a compliance issue comes up? So the question that would ask would be, where do they form, in the plant or the distribution system? Now, answering those questions would include monitoring the plant finished water, monitoring in the storage facilities, monitoring consecutive system entry points, increased monitoring, non-regulatory in warmer months, repeating that monitoring seasonally to track how seasons and temperatures affect formation. Is it possible to switch or blend sources to reduce TOC, NOM, formation potential? Can any operational changes in using sources or blending sources help reduce DBP formation? Which species or which component dominates? Is it TTHMs or HAA5s, which would also indicate where management in the distribution system should focus? And then setting plant effluent disinfection byproduct goals, non-regulatory, along with distribution system targets so that operators can focus on adjustments to reduce disinfection byproducts. Another proactive component would be treatment optimization, including coagulation and settling processes, changes to those processes to reduce TOC, NOM, consideration of coagulant dose and type, the pH during coagulation, and any operational practices in coagulation that could reduce precursors. Biological filtration is capable of reducing NOM precursors, and obviously pre-chlorination or pre-disinfection has to be stopped, but no pre-oxidants are needed. Changes in disinfection practices. If disinfection, raw water or settled water is being disinfected, can it be eliminated or reduced? Can injection points be removed? However, during treatment optimization and changes, simultaneous compliance and the secondary impacts of those changes, any changes, have to be considered. That would include meeting disinfection or CT requirements, any inorganics removal that the plant may be trying to achieve, and then lead and copper rule and corrosion control considerations in the distribution system. Distribution system optimization can also play a role in reducing disinfection byproducts. Optimization activities would include monitoring the chlorine residual in areas of suspected high water age, setting distribution system disinfection byproduct goals lower than the MCL, again in combination with treated water, lower treated water disinfection byproduct goals, and finding management or operational strategies to meet those goals. Water age management, which would include tank fill and drain cycles, removing or reducing excess storage, automatic flushing, and then focused flushing programs such as unidirectional and targeted flushing programs. Again, with considering simultaneous compliance and secondary impacts, possibly reduced pressure and more difficulty maintaining residuals in the system. Quickly cover the stage 1 disinfection byproducts, which carry over. They remain as stage 2 is implemented. TOC source water monitoring before treatment every 30 days, it's reduced quarterly. The TOC requirement of less than 4 remains a criteria. I won't go through in the interest of time, which is now short. Systems using chlorine dioxide continue to be required to monitor for chlorite, compliance based on the arithmetic mean of sample sets at the entrance of the distribution system. Bromate continues to be required for those systems using ozone, monitoring monthly at the entrance to the distribution system. Chlorine dioxide monitoring requirements remain, measuring again at the entrance to the distribution system with monitoring based on the results to the maximum residual disinfection level. There is an acute violation component of chlorine dioxide, which hopefully no one has to deal with. Disinfectant residuals for the chlorine and chloramine, again the MRDLs remain, measuring residuals at the same time and place as the TCR and revised TCR. The residual monitoring carries over to the RTCR. Distribution systems system samples collected for compliance with requirements for surface water systems. That is, those collected at the same time as the TCR samples can be used for compliance. And compliance is based on the running annual average of monthly samples. Continuing requirements are DBP precursor monitoring for conventional systems. Again, TOC requirements used to determine enhanced coagulation. The continuous precursor monitoring, again, TOC removal is an indicator of precursor reduction prior to disinfection, reducing the potential for formation of DBPs. It remains as a parallel requirement to TTHM and HAA MCLs in the distribution system. And with that, I will finish and turn it back over to Tom. Thank you.
Tom or Michelle, are you there?
Sorry about that. A little technical difficulty, of course. Thank you very much, Mike, and we'll move on to our second presenter in short order. A couple housekeeping activities. Again, if you have any questions, type them into the question box as soon as you think of them, and we'll kind of sort them as best we can and answer them at the end of the second talk. If you have more than one person that's in your room, if you could put that in the question box, how many people are in your room, if you haven't already, that would be great. It helps us count the number of people who are on the webinar and justify how many people it's reaching and justify the importance of this webinar. And finally, just to note that slides are attached in your handout tab. So if you want them just to follow along or for documentation purposes or for records, for your own records, they're at your disposal. So on to the second presentation is Jolynn Leslie. Jolynn is our regional engineer for the Washington State Department of Health Office of Drinking Water. She's a civil engineer with over 16 years of experience working with water systems. First as a Peace Corps volunteer in Honduras, working on mainly small gravity-fed water systems. For the last 14 years, she has been a regional engineer and is responsible for implementing the state's drinking water program. She is also the regional DBP lead for the Northwest Regional Office. She is an active member of AWWA and volunteers both domestically and internationally for Water for People. So with that, I'll hand the podium over to Jolynn.
Great, thank you, Tom. I'm very happy to be here this morning to present and share our experiences here with some small systems in Washington State. So first off, I want to share our Office of Drinking Water mission here in Washington. We work with others to protect the health of the people of Washington State by ensuring safe and reliable drinking water. Today I will start with a brief snapshot background of DBPs here in Washington State, give some examples of some installed treatment, modified treatment, and then go through some operational changes. So just to start with a brief snapshot, we have both surface water and groundwater systems here that have had DBP MCL exceedances, but the majority of those are actually groundwater. And as you can see, these systems are small to very small, and the NTNC systems include an elementary school, a church, a power generation facility with 380 employees, and a national park lodge. And we do tend to have more THM exceedances than HAAs. So here's a map of Washington State, and you can see the little blue dots there are where we've had some past DBP problems. They have either installed treatment or modified treatment to come back under the MCL, or they may have made some operational changes. The red dots are the places where we still have some issues. And so you'll note that there are some regional clusters, and the Northwest region, which is where I'm located, has the majority of the systems. And as you'll see later, there's more than just geographic locations that many of these systems have in common. Probably the biggest commonality with surface water systems is that their source water is not always the best quality, and most of them use small impoundments or streams. And they are generally high in TOCs, but not in all cases, as you'll hear later. As I was going through collecting information for this presentation, I discovered that many of the groundwater wells that have DBP problems have very similar water qualities. And we hope that this can maybe not only help explain why these systems are having DBP problems, but maybe also help to come up with treatment solutions and experiences that can be shared. And so for these systems, they generally have low to moderate TOCs, but not in all cases, as you'll see later. And I'll go through in more detail some of the water quality characteristics that these systems share a little later. Some examples of treatment that have been installed here are aeration, which is post-treatment, and that is both passive and active aeration, active being something more like a slat tray aerator or packed tower aeration, and passive being just spray nozzles installed into storage tanks. And then we do have a couple systems that have GAC installed both for precursor removal and for DBP removal after filtration. And we'll also look at a couple systems that modified their treatment either through filtration or by changing coagulant or oxidant. So to start off with, the first system that I'll go through is a surface water system. It serves a small private community, and THMs are the main problem. So they actually had a rapid rate package plant, and they installed active aeration through a packed tower aerator. THMs were the main problem. They also have an RO unit that they use in the summertime to supplement the surface water source. There are 70 connections on this system with a full-time population of about 90, but it does serve a lot of vacation homes and snowbirds. It's an association that has a volunteer board and a contract operator, and you see here that the TOCs can be pretty high during certain parts of the year. So like I said, they installed a packed tower for aeration with constant recirculation at 25 gallons a minute. This is their surface water source. It's a small pond, and it's refilled by runoff and rainwater, and there is no stream inlet. They do have a screened intake with the option to modify depth of the intake, but that is usually not done. Here's a picture of what they installed for their packed tower aeration. Their storage tank there is to the left. The white PVC pipe is where the packed tower is, and on the right is the pump building. And so it's installed on the inlet to their 80,000 gallon storage tank. And this is an example of the packing modules that are inside the packed tower. Here's a picture of their system, the blower, recirculation pump, and tanks. So they, like I said, they have constant recirculation at about 25 gallons a minute. They have the recirculation tank and a 75 CFM blower. So the pump on the right returns water from the drainage tank to the storage tank, and the pumps on the left pump water from the clear well to the pack tower. Their highest samples were prior to the stage 1 DBP rule under the old THM rule, and their highest they ever got to was 380 micrograms per liter. They were back on routine annual sampling at one point after installing the pack tower, but since they made that change, they changed their rapid rate plant to a slow SAM plant, and now both their THMs and HAAs have both skyrocketed again above the MCL. So they're going to have more work to do here in the coming future. The next system I want to talk about is also a surface water system. It serves a resort community. The surface water plant includes potassium permanganate, a coagulant, muriatic acid for pH control, filter aid polymer, absorption clarifier, mixed media filters, GAC, post-chlorination, and caustic soda for corrosion control. As a resort community, it serves a hotel, cabins, and rental homes. The full-time residential population is about 329, but the part-time population more than doubles during the summertime. And while it's not used for the DBP monitoring population, they also get about 1,300 transit visitors per day during the summer peak. Prior to installing the GAC, they were already getting about 56% removal of TOC through the existing plant, but they still had ongoing problems with THMs and every now and then HAAs as well. So they installed the GAC in 2009, and it's 2 units in series post-filtration. Here's a picture of their raw water. Their source is a pond. It's very high in humic matter, has manganese at about 2.5 times the secondary MCL at 0.12 milligrams per liter, moderately hard water at 100 milligrams per liter hardness, and conductivity at about 288 micromoles per centimeter. Just an interesting aside, a limnologist from University of Washington completed a study on the pond a few years ago and found anoxic groundwater seeps with iron hydroxide deposits, Daphnia, Eurasian milfoil, and benthic cyanobacteria. A new dam was just installed a few years ago that provides a higher elevation overflow, and the system is currently working on a strategy to manage the transition of the lake due to this operational change. And it's looking like the higher overflow may actually cause the GAC to be used up sooner. They have 2 tanks, each are 5,200 gallons and hold 20,000 pounds of carbon. The design flow is 200 gallons per minute with an empty bed contact time of 22.6 minutes. The system is located on an island that is only accessible by ferry, private boat, or plane, and so getting equipment and trucks over for service and maintenance of the GAC is a little more work than normal. Here you see a GAC changeout, and so part of the discussion with this system during the design phase is, how often they should change it out. Do they wait until the LRAA is approaching or over the MCL, or do you do it sooner? So the approved design for this system actually specified that it should be changed out after the first high quarterly sample above the MCL. And at about $36,000 for each change out, the design expectancy of the life of the GAC was about 470 days. So they had been getting about 2 years life, so actually much greater than what the design expectancy was. But with the changes at the dam, this may not be quite as long in the future. And part of the pilot study for this, for the GAC system also included looking at a correlation between UV254 and TOC. And so it assumes that removal of TOC reduces DBPs proportionately. They do have a target TOC of 2 milligrams per liter, which is approximately 1/4 of the treatment plant filter effluent TOC level. And so they are actually using UV254 to help control their coagulant dose to meet that target TOC of 2 milligrams per liter. They're taking weekly pre- and post-GAC samples to analyze for UV254, monthly THM and HAA samples for tracking. So they're actually going above and beyond what they need to do to stay on track. They did reduce their levels of both THMs and HAAs, and treated water TOC was cut from about 10 to 15 on the raw water by about a half to a third. So the system is working well. The next system I'll talk about is a groundwater system. They have installed active aeration in the form of a flat tray aerator. Their TOCs are relatively low. THMs is the main problem. And they did pilot GAC, but found that it was cost prohibitive to do that. So this system does have raw water manganese at about 3 times the secondary MCL. Their treated water manganese is right around the secondary MCL. This system does have high chlorides at about 178 milligrams per liter, very hard water at 280 milligrams per liter, and conductivity at about 1,191, and total dissolved solids at 640 milligrams per liter. So not really the best groundwater quality to begin with. So here's a picture of the flat tray aerator that they installed. The aeration was also installed for lead and copper treatment, and with a target pH of raising it to about 8 to 8.2. It's a 6-tray aeration unit, constant recirculation at about 25 gallons a minute, 150 CFM blower, and the design target was to have 45% bromoform removal on a single pass. And as you can see from the pilot results, they actually did get very good bromoform removal, which is the heaviest and hardest to remove by aeration. So this treatment turned out to be very successful for the system. And as we've been finding, the active aeration using flat tray aerator or pack tower or some other designed aeration is much better than the simple passive spray aeration. So this system did reduce their THMs, and they are back on routine annual monitoring, and they also are back in compliance with the lead copper rule. So now I'll go through some examples of modified treatment. Again, these are both surface water and groundwater systems. We'll go through some treatment technology changes and also some modified treatment. So the first system is a surface water system. They had stage 1 THM violations, but the MCLs have not had a violation, though they have had individual samples above the MCL. This is the largest system that we have dealt with that have had an MCL violation, with a population of about 3,800. So they use aluminum chlorohydrate to address the TOC, and they take TOC samples and adjust the ACH dosage based on TOC levels. And then they did also change from a rapid rate plant to a membrane filtration plant. Here's a picture of their 2 sources, the main impoundment on the left and the secondary reservoir on the right. And then there's also a local creek that supplements the main impoundment on a seasonal basis. Both sources are characterized by low alkalinity, which is pretty common here in the Pacific Northwest. Some iron at about 0.1 to 0.6 milligrams per liter, and very little manganese. They did have some luck with their treatment plant changes, but just in the past couple months, it seems like their DBPs are increasing again, so they may need to do more work on getting that under control. The next system is also a surface water system. They have a population just under 3,000. And again, so this one, the HAAs were the main problem, but they did have some individual THMs above the MCL, just not their LRAA. The water leaving the treatment plant was already close to the HAA MCL. They do have high algae, and their raw water TOC, as you can see, is relatively low at 1 to 2 milligrams per liter, but they do have some challenges that I'll describe next. So the treatment changes they made is they modified their flocculation stage with plate settlers, stopped pre-chlorination, and are now using enhanced chlorination. This is their river intake. It has 3 screened inlets with 1/4 inch stainless steel screens that are removed and cleaned every year in the fall when they become fouled with leaves. The intake faces upstream, but they still have problems with sediment building up in front of the screen, which can significantly limit flow. Sediment removal is performed on an as-needed basis, which is usually several times during the winter. 8 feet of sediment is typically removed at the inlet. The wet well is vacuumed out once per year to also remove sediment. Kind of interesting, they also have had problems with river eels fouling the raw water pumps. So when the operator observes a decrease in raw water flow at the plant, the pumps are checked and eels or other objects are removed. With their treatment modifications, they've been able to come back into compliance with both THMs and HAAs. Now I'll go through some operational changes that systems have found to be successful here. So as Mike had mentioned, routine flushing can be very useful. We did have one system, though, that was flushing the day before they would, and now our guideline that we give to systems is that if they do flush on a quarterly basis, they should plan to flush at least 4 to 6 weeks prior to collecting their samples so they don't skew the results downward. We do have a few systems that are doing weekly flushing, and this probably seems luxurious and wasteful to some areas of the country where water is more scarce, but they're finding that that's what works best for them. We do have systems that are using some storage tank management. We have systems that are seasonal, that have vacation homes where water usage is lowest in the winter, and DBPs would actually spike in the cold winter because water usage was so low. They have gone to a winter operational mode where they lower the tank levels in the winter to help address that problem. And we do have some systems that are blending, but they really need to pay attention to when they have to blend surface water and groundwater sources to make sure that they're staying below the DBP levels. One system that has both surface water and groundwater measures the TOC in the blended water to make sure that they're staying below the levels. So I wanted to talk a little bit about sort of the groundwater systems here. As I said before, the majority of the systems in our state that have DBP MCL exceedances have been groundwater systems. And as you can see, the water quality is not real great from groundwater. Hard to extremely hard water, high iron and manganese conductivity, TDS, and generally low TOC. And I think this low TOC is very interesting and worth more investigation. Another thing that we have in one county, we have a lot of relic groundwater. Relic groundwater being basically really old, ancient groundwater that is very hard with lots of minerals. The county hydrogeologist for that county was developing their seawater intrusion regulations several years ago, and he discovered that many areas that had high historical chlorides and conductivity were not always due to seawater intrusion, but to this relic groundwater. In another county where we've had a lot of problems, the wells are drilled in fractured bedrock. TOC is relatively low to moderate at about 1.1 to 4.7 milligrams per liter. This is the county where we've had some successful installations of the active aeration, and some of the other systems in the area are also looking at that option. I did want to share a couple of interesting little tidbits. We do have one system that purchases all of their water from Metro Vancouver in Canada. And and Metro Vancouver completed construction of their new Seymour Capilano filter plant in 2010. And once that change happened, the consecutive system, their THMs dropped quite significantly from 134 micrograms per liter to 23 and 41 micrograms per liter. So the system themselves didn't make any changes, but with the addition of filtration on the supplying system, it pretty much solved their problem for them. We do have another system, surface water system, that installed a brand new treatment plant. They did change coagulant. In their old plant, they had a HAA5 problem and a copper problem. They installed a new plant, changed the coagulant, and their problem changed to THM exceedances and lead above the action level. They did also get a new operator in that time, and their inactivation ratios for their treatment plant were running at about 9 to 15 with the old operator. And with the new operator, they've reduced those down to about 2 to 5. They increased pH for corrosion control and changed back to their old coagulant. And they have been successful with those changes. So just maybe a humorous story. The previous mayor of this system, when he heard that with his population just above 500, that put his system into more frequent DBP monitoring, he famously joked that maybe he should go burn down a few houses. He didn't do that, but you know, luckily they're back in line with their DBPs now. And just one other interesting note, we are just now finishing up on the last quarter of a year-long DBP formation study in the 2 counties that have the extreme groundwater quality. As of yet, we don't have any conclusive evidence information, but it seems the initial information seems to be pointing towards humic organics in the groundwater. So we'll hope to learn more as we wrap up that study. Some of the recommendations that we give to systems are to really know your water quality. TOC, DOC, I think that's good to know. It might be helpful to know if you've got more plant organic material or if there's other types of organic material that's causing the TOC. Look at UV254. It's a lot cheaper to run UV254 than it is to run THM and HA samples. And you know, it's been shown that you can establish a good correlation between UV254 and TOC and TTHMs, and that can be really useful in troubleshooting your system. And I'm also a proponent for knowing more about your water system through water quality. So as Mike mentioned, you know, looking at free and total chlorine at the entry point, at the top and bottom of your storage tank, at the end of your distribution system, and the same time and location as your DBP samples. And same thing for pH. You know, I don't know if many systems tend to monitor for pH, but you know, higher pH, you tend to have higher THMs, so that might be an important factor to look at. And again, temperature can be an important factor, looking at the top and bottom of your storage tank, and then also, again, at the same time and location as your TBP samples. And then we, you know, we work with operators to make sure that they're using proper sampling techniques. Make sure that they flush the line before collecting their samples. You don't really want stagnant water in your sample. Don't overfill the bottles, especially if there is some sort of neutralizing agent in the bottle, and be sure to put the samples on ice. One other thing that we have done here in this region at least is we've done technical assistance field visits where you group operators together to help with knowledge sharing, you know, sit down and explain the OEL to them, the operational evaluation level, and make sure they know how to calculate that, and get them thinking about changes they can make, and prepare them for any treatment or notification requirements. So generally these have been a small number of people, mostly grouped together geographically, and we have also shared you know, contact information amongst them to try to get greater interaction between those operators. So that wraps up my talk. Thank you for this opportunity.